Hello everybody, my name is Garrett and this is the Unit 2 Talk It Out. In this session we will be going over a problem regarding most stable structure with lowest formal charges. And for this I will be doing Chapter 10, Problem 26, and the problem reads, phosgene is a colorless, highly toxic gas that was employed against troops in World War I and is used today as a key reactant in organic synthesis. From the following resonance structures, select the one with the lowest formal charges. And as you can see here, I have drawn out each of these resonance structures and I color-coded each component just to make them easier to distinguish, I guess you could say. And here we have our formula COCl2, which of course is phosgene. And there are minor differences between each structure with the placement of the double bond, which is very important when it comes to finding the best structure, or the most stable structure, I should say. So when we want to find the formal charge of a molecule, we need to write out each component one after the other, trying to find the charge of that individual component or element, I guess you could say. So when we are trying to find the formal charge, we go by this format. So you use the number of valence electrons for that element, which you find in the periodic table, minus, and then in parentheses, the number of non-bonding electrons. So these guys out here, you see these dots, of course, these are the non-bonding electrons. And then you add those to the number of bonding electrons for that specific element. So with carbon, you see that these are the bonding electrons right here. So let's start with carbon. Let's walk through it. So carbon on the periodic table has 4 valence electrons, and we subtract that, and then in parentheses we look at this first structure and we see that there are 0 non-bonding electrons around this element. So we put a 0 right here. Then we add that to the amount of bonding electrons, this number right here. And when we look at here, we see 4 lines right here, okay? Now, each line typically, or they represent 2 electrons. However, the reason why we don't put 8 electrons right here is because half of the electrons go to one element or component, and half go to the other that is connected to that. So for carbon, while there are 8 electrons in total, we have to divide that by 2 to find the amount that I guess are owned by carbon. So 8 divided by 2 is 4, so that's why we put a 4 right here. 0 plus 4 is 4, 4 minus 4 is 0. So now we know that the charge for carbon is 0. So now we move on to oxygen in this number 1 structure. We know that oxygen has 6 valence electrons, and moving to inside the parentheses, we count the amount of non-bonding electrons. 2, 4, 6 non-bonding electrons added to that single bonding electron right here. 2 divided by 1, 2 divided by 2, excuse me, is 1. So 6 plus 1 is 7. 6 minus 7 is negative 1. So we now know that oxygen has a charge of negative 1. Moving on to the chlorines. The chlorine on the left this time is the one with the double bond. So that is why we have to distinguish left and right, because these are 2 different components. They may be the same element, but they have different bonds and different amounts of non-bonding electrons. So we know that chlorine has 7 valence electrons, For this left side chlorine, we see that there are 4 non-bonding electrons, 4 right here, and then we add that to the 2 bonding electrons. 4 divided by 2 is 2. So 4 plus 2 is 6. 7 minus 6 is positive 1. And we find that the chlorine is positively charged by 1. Moving on to the electron on the right, 7 valence electrons. It's not going to change the amount of valence electrons because they're the same element. And moving to the non-bonding electrons, we count 6 right here, 2, 4, 6. 6 plus that 1 single bonding electron is 7. 7 minus 7 is 0. And so we come to the overall charge, which is 0 because this negative 1 and this positive 1 will cancel out. Moving on to the second structure. This one has a double bond on the oxygen on top. And with the carbon, it's going to be the same charge because in each structure, you can see that each carbon has 0 non-bonding and 4 bonding electrons. So 4 minus 4 is 0, no charge. And this is where it starts to differentiate from the first. The oxygen this time is the double bonded. And we see that in this oxygen, there are only 4 non-bonding electrons, while there are 2 bonding electrons. 4 plus 2 is 6. 6 minus 6 is 0. And moving on to chlorine, now you see that there's only 1 chlorine spot this time. And this is because the only difference between the chlorines here are that they are mirrored, and that there aren't going to be any differences in non-bonding electrons or bonding electrons. They both have a single bond, therefore they both have the same number of non-bonding electrons. So we can just do one spot right here for chlorine. 7 valence electrons minus 6 lone pair electrons or non-bonding electrons plus the 1 bonding electron for chlorine. 7 minus 7 is 0. That brings us to our overall charge, which is also 0. And moving on to the third and final structure, very similar to the first structure, except it's mirrored this time. So with carbon, of course, it's going to be neutrally charged. 4 minus 4 is 0. Oxygen this time is going to be the same as the first structure. 6 minus 6 non-bonding electrons plus 1 bonding electron. 6 minus 7 equals negative 1. Now this time we're going back to the left and right chlorine. This time on the left, chlorine with 7 valence electrons minus 6 lone pair electrons plus 1 bonding electron. 7 minus 7 equals 0. And then we move to chlorine on the right. 7 minus 4 non-bonding electrons plus 2 bonding electrons. 4 plus 2 is 6. 7 minus 6 is positive 1. That brings us to the overall charge for the third and final structure, which is 0. So still neutrally charged, except, and the reason that is because this negative 1 and this positive 1 cancel out. So all these structures have a neutral charge of 0, but even though they are all neutrally charged, we can still determine which is the most stable structure. And how we do this is we look at how much work each structure has to do to become neutrally charged. And what I mean by work is these numbers right here, these charges, these individual charges. If the charge is not 0, that means that component is doing work. So as we can see here, for example, the oxygen in the first structure right here is doing work. This negative 1, that is work, that is energy. This chlorine on the left, this left-sided chlorine right here, this is doing work and there's energy involved. This positive one. This energy is, this molecule is doing work to become neutrally charged. This negative one and this positive one have to cancel out just to become neutrally charged. And with this second structure here, we see that none of these components have to do any work to be neutrally charged. There's no negative and no positive charges just to get to 0. And with this third structure, it's the same as the first. There's a negative one and a positive one. There's energy involved. And this molecule, as well as the first molecule, must do work in order to become neutrally charged. That is why structure number 2 is the most stable structure, because there's no work or little to no work involved to become neutrally charged, while the first and the third are doing work to cancel each other out in order to become neutrally charged. And that is it. Thank you for joining me. Have a nice day.